Okay. Anyone have any questions about the homework assignment? Things that were confusing?
Could you just tell us the answer so we know we got it right?
Let's see. I haven't done it yet. But I could tell you how to do it. Oh, yeah, it's not due till the end of class. And
We're supposed to assume that this field we're talking about, the angle at 45 degrees, right? Not the one attached to this.
that's right. That's right. Yeah. So really, like sort of the overall approach is you you isolate the hanging mass with those hanging pulleys to figure out the tension in the cable. And then once you have the tension in the cable, then you go look at the connection with the wall, use a unit vector to figure out the direction that that force is applying to the wall, you know, and the magnitude, you know, is the cable tension. So that's the approach. Okay, so at the end of last class, I gave you this problem, gave you a little time to think about it. There's this guy leaning against the wall. Holding on to this wheel thing just to make it clear what kind of force is being applied there. Down at his foot, it's not super clear. But I think one choice is considerably better than other choices. Okay. He's wearing clothes, in case there are any children who watch this video. Okay, and between the center of mass of the system and where the foot touches the floor is 1/2 meter. It's another 1/2 meter to the contact with the wall. And the height to the contact with the wall is 0.8 meters. Did anyone get an answer for this problem? Does anyone think that the way you indicate yes is by not raising your hand? Okay. You did get an answer? Oh, shoot, I forgot to calculate that. We'll have to calculate that. And what did you get for forces? 784. For yeah. Nice. That's great. That's what I got too. Okay, so I think what that means is sort of the first tricky question is, and maybe the only kind of question where there's such a thing as another choice that you could make a good argument for. So here's our free body diagram. Is what kind of joint is there? Well, first let's do the easy one. What kind of joint is there between the wheel and the wall? That's a roller, and so we know that there's going to be a force acting this way, right? And I'll just call that R. And that's the only load acting there. But what kind of loads are acting at the foot? Well, you could think of it as probably the best way to think of that is a, what do you call it? Just I gave it in the notes. There's a surface with friction, right? So if that's the way you treat it, then the load is just going to be a force vector. And I think that's the best way to do it. I'll call that force on the person by the ground. You could also, make an argument that that part of the foot, you see how the forefoot is sort of bent there. That can provide a little bit of a couple, a little bit of prevention of rotation, right? If you think about it. But overall, when you think about what's what's really keeping this object from rotating, I think it's pretty clear that this person couldn't just stand there like, if he lifted up that roller, he's not going to just stay there like that, right? So in that sense, the prevention of rotation that your foot provides is sort of negligible, okay? And that's why in this case, I'm going to treat it this way, but it sort of gets to something that comes up in real problems all the time. None of these mathematical idealizations are perfect descriptions of what's going on. It's just a matter of what is the most accurate, okay? And this is the best way to do it, I would say. Also, if you treated it as if the ground was applying a couple here, this thing becomes a statically indeterminate system, right? Because you have two unknown loads, a third. That takes up all your equilibrium equations. And then you also have that unknown couple. That's a fourth unknown, 3 equations, so you couldn't solve it. Did you? Okay, so let's do it this way. So is this free body diagram done? One more thing, gravity, right? Yeah. And I think I said 80 kilograms. So that force is 784.8 newtons. And now we can go to, well, now I'm going to go to filling out that table. And in order to do that, I have to choose a coordinate system. I will choose it. I guess I chose it right at the contact with the foot. There's no right or wrong answer for that one, but if you choose the coordinate system at the foot, then you don't have to deal with the unknown force vectors producing moments. Well, if you choose that as your about point, I guess is. Let's move on. Okay, so where the force is applied, the about point, rho, and then the force vector, and then the moment about the about point. So I'll start with the force applied at the foot. It's located at the origin, and I'm going to make that the about point. So the rho vector is 0. The force vector is FPGX, FPGY. And so the moment is 0. Next, I'll go to the weight force. That is applied at, the x component is 0.5. And what's the y component? It actually isn't 0.8. I mean, if you look at it, we don't know what it is, but I'm going to use the fact that you can move a force on a rigid body anywhere along its line of action, and it won't affect the problem. And I'll just make that 0. Okay? Its line of action is vertical, so you can move it up or down anywhere you want. The about point is zeros. So rho is 0.50. The force vector is 0, negative 784.8. And so the moment about A is 0.5 times negative 784, so negative 392.4. And by the way, if you're trying to eyeball this to sort of get a sense of whether your answer makes sense, a negative moment means that about your chosen about point, this moment would tend to produce a clockwise moment. And that's what would happen here, right? If this was a hinge, the only force was this, it would make the body spin around the foot like that. Okay. So that makes sense. And then the last one is that force R. That one is acting at 1 meter, 0.8. The about point is 0, 0. The row vector is 1.8. The force vector is negative R, 0, right, because it's acting to the left. And so the moment about A is 0 minus 0.8 times negative R, so 0.8 R, positive. And now we can go to Newton's laws. So F PGX F PGY plus 0, negative 784.8 plus negative R, 0 is 0, 0. And the rotational Newton's second law about A is negative 392.4 plus 0.8 R is equal to 0. And if you solve that system of equations, you get R is 490.5. And the force vector on the person by the floor is equal to 490.5, 784.8. Any questions about that? Yep.
How did you find coordinates of the point where force of gravity was applied? Isn't it 0.5 and 0.8?
Yeah, right.
I just got confused.
Right. So remember last time I mentioned that without changing anything about the problem, on a rigid body, you can move that force anywhere along its line of action. So even though we don't know what the y component is, we know it won't change anything to move it up or down this line. So that's what I did. I just moved it down to 0. Okay, yep. There is one set of practice problems up on rigid body statics, so you should get to those as soon as you can. And I'm about to put another set up, and I'll get the solutions up to those as soon as I can. So you should get on that. I think maybe some of you found the easy way and some of you found the hard way that it's a lot easier to do, it's going to be a lot easier to do those problem sets if you've spent some time already familiarizing yourself with the material by doing the practice problems first. So I would really recommend that. Get to the practice problems right away, and then the problem sets you'll have sort of a fighting chance against them, you know. Okay, so now we're moving on to chapter 5. Which is centroids. And a centroid is just a geometric thing, but it has two important purposes for us. It is how we calculate where the center of mass is. And it also is necessary for doing calculations involving distributed loads. And I'll talk about both of these in this chapter. And to introduce this, for rigid bodies, and by the way, this is sort of something interesting. Once you draw your free body diagram, no matter what material you're talking about, you're treating that as a rigid body, okay? Before the free body diagram, you know, you treat rigid bodies and deformable bodies differently. But once you've chosen your free body diagram, it's a rigid body approximation that you're making. And with rigid bodies, you can often substitute one set of loads for another without changing the problem. So of course you could substitute one set of loads for another, but it's the fact that it doesn't change the problem that's good. You know, right? Mike, help me out. Thanks. For example, ones that we've seen are the thing we did right here. You can move a force along its line of action. One we haven't seen yet that will be useful in dynamics is that for any set of loads you can come up with, I mean, tons of load, infinitely many loads, or 20 different couples and 20 different forces, you can always reduce that set of loads any set of loads can be replaced by a single force vector at the center of mass and a couple. But the one that we're most used to like one you're so used to that you don't even really think about as a substitution is replacing the infinitely many gravity forces that are acting on our body, on any object, with a single force vector acting at the center of mass. Okay? That's a substitution. It's not like gravity does a calculation of every object's shape and then figures out where the center of mass is and applies a single force, right? What it really does is just pull a little bit everywhere, Everywhere there's mass, it pulls a little bit. And that's called a distributed load. And gravity isn't the only thing that produces distributed loads. For example, our idealization of the contact between this wall and this roller is that it happens at a single point, but that's not really what happens. It happens over some amount of distance, and over that distance is a distributed load. There's a little bit of force at every infinitesimal distance, and it adds up to a finite force. And it shows up in problems like this. Say that you have an object that's covered with a big pile of snow or something. This region over here is yellow snow. Stay away from that. And say this is a building or something that's being designed. You need to deal with the fact that this weight's going to be here. You need to calculate what kind of loads to expect. So how would this force, the weight of this snow, present itself? Well, you could think of breaking it up into a bunch of strips, okay? And think of these strips like when you're defining an integral. Think of limiting these, taking the limit of these strips as they go to 0. Then the gravity force of each one of these strips would be the density of the snow times gravity, and then times the, in a two-dimensional case like this, times the area of that strip. So the height times that infinitesimal thickness. And so this would be one way to write it. This will be represented in problems like this. You'll see the object, and you'll see a profile like this that shows a bunch of downward vectors. And it'll say something about the function describing the height. And the height of this, in this case, is gravity times the density times the height, is given in newtons per meter. Okay, and that's represented by the height of this graph. Okay, so this h is the height of the snow, right? The height of this picture gives that distributed load at any point. Let's see. Let's say the height of the function at any point represents the distributed load. What we want to do with this distributed load, once we draw our free body diagram, is, well, you could go and draw each of these forces on your free body diagram, but there's infinitely many, so you'd be there a long time, and you need a thin pencil. So what we want to do is treat all of those distributed loads as a single load acting at a certain point. And it turns out that that certain point where it's going to act is at the centroid of this shape, okay? So in your free body diagram, we'll treat the distributed load as a single force vector acting at the centroid. So that's a motivation for knowing, how to calculate a centroid. The magnitude of that force, by the way, this I guess comes up later. But the magnitude of that force vector is the area of that distributed load, okay? So if we calculate the area of this shape, it tells us the resultant force vector. And if we calculate the centroid of this shape, it tells us where this force vector is applied. Okay, so here's the definition of the centroid in 2 dimensions. The area of the shape times the centroid vector, which is, I'll call it capital X bar and capital Y bar, is equal to the integral over the entire area of the centroid of each infinitesimal area, which is a vector, times the increment in area. Most of the time, you're not going to have to use this formula. Most of the time, we'll use some simple formulas. And you already know, like, you already calculate in your head the centroid of rectangular shapes and circular shapes, right? There are some simple shapes like that you almost know intuitively. There are some other simple shapes that I'll give you formulas for. And you can build up more complicated shapes using the centroids of those simple shapes. But occasionally you'll have to use this integral formula. So here's an example of how this is used. Anyone have any questions about that formula?
What did you call the vector?
This?
Yeah.
That's just the centroid location. Oh, and I called this equation 5 in my notes. one thing interesting about this, you'll see this in a few examples, is this is true no matter what coordinate system you choose. Okay, you have to, so we have to define a coordinate system, and don't worry about like, oh, am I choosing the wrong one, or it'll come out the same. It'll point to the same point. Okay. All right, so let's calculate the centroid of this shape. Right triangle with a width of b and a height of h. I'll use this as the coordinate system. Anybody know where the centroid is of this shape? Yep, exactly. 2/3 b, and then how about the other way? It sort of has a symmetry, so then it's just 1/3 of the way up too. Okay, so it's like where this line meets this line. Okay. All right, so to do this, I'm going to, like, in order to calculate this integral, I'm going to express this line as a function. So y is equal to, it goes through the origin of this coordinate system, right? So y is equal to rise over run times x, h over b, x, right? And now my increment of area, like, look at what this formula says. I have to choose an increment of area, and then for each one of those small infinitesimal areas, I have to figure out what the centroid is of that shape, okay? And then I have to integrate that, and it'll give me the area. You know, I just have to divide that answer by the total area, and it'll give me the centroid. Well, we know how to calculate centroids of rectangles, or we know what those centroids are. You're used to doing that. So I'm going to define my infinitesimal area in terms of rectangles. Okay. The height then is y. The width is dx. And the centroid then is of the infinitesimal area is x, right? Whatever x we're at. And then y over 2. You see that? It's halfway up the height, and it's at the, it's just wherever this thin little strip is. And I'm going to do this integral kind of, at least in my notes, I did it in like a vector form. But don't get thrown by that. I'm just doing, it's two separate integrals that I'm sort of doing at the same time. That's all. Okay, like you can do it in two pieces. Do the x integral and do the y. This x centroid, calculate the y centroid separately, and then put it back in vector form. Okay, and what's the increment of area? dA is equal to, did I already do this? It's just equal to y dx, right? Yeah. Which then we can substitute this in, and it's equal to h over b x dx. Yikes. Okay. The area of this shape, get that out of the way, is just 1/2 base times height. So our formula says 1/2 base times height times the centroid is equal to the integral. As my independent variable, when I define this function, my independent variable is x. So the boundaries of integration are going to be my x boundaries. So 0 to b in this case. Then we have our centroid, which is x, and the y centroid is y over 2, and our y is this. So hx over 2b. Is everyone following this? Because if you're not following right now, this is going to be 5 minutes of boring chatter. Remember integrals? Came up in calculus probably. Okay, and then multiply. So that's our centroid vector for our increment of area. Then multiply that by our dA. So that's h over b. This is just a scalar. And I'll rewrite this now as the integral from 0 to b. Multiply all these scalars into the vector. So we get h over b x squared dx. And in this one, we get h squared x squared over 2b squared dx. Okay. So you can see how that's just two different integrals that I'm solving. So if you integrate these, you get, what do you get on this one?
H over 3b x cubed.
Right. Thank you. H x to the third over 3b. And for this one, you get h squared x to the third over 6b squared. Right? And we're evaluating from 0 to b. And so if you do that evaluation, 1b cancels here, you get h b squared over 3, right? And over here you get h squared b over 6. You agree with all that? Okay, now let's cancel some stuff. So we have this is equal to this, right? So we can cancel a b and an h from both of these. And then multiply both sides by 2 to get the centroid by itself. And we get x bar, y bar, the centroid of this shape, is equal to 2b over 3 and then over here h over 3. Okay, so the centroid then is, that's the 2b over 3 is along this line, right? 2/3 of the way to the end. Like 2/3 of the way to the fattest, to the tall end. And the same thing here. It's just that we started at the fat end instead of starting at the point, right? So 1/3 of the way here. And so the centroid, which also would be the center of mass of this shape, is right there. What? If it's homogeneous, if it's the same material, that's right. I'll bring that up. Yeah, so if this shape was made out of tissue paper except for a piece of steel right here, then this isn't going to be the center of mass. That's a really important point, even though it was presented in sort of a smart-ass way. So the centroid is the center of mass if you have a homogeneous material, the same material all the way through. And I'll talk about how that changes if you have, different materials in different places. So you won't have to do too many of those integrals, but you'll have to do a couple. So here are a couple things to keep in mind. First, just like we came up with this formula for the centroid of a triangle, of a right triangle, there are formulas in the back of the book for a lot of common shapes, including that triangle formula. And if you don't have the book or you have a different book, you can Google it, It's easy to find those. And second, as long as the body that you're looking at is a single material, is homogeneous, the centroid is the center of mass. In this formula, so I gave you the 2D version, but the 3D version is exactly what you would guess if you were asked to generalize to 3D. The volume of the object times the three-dimensional centroid is equal to the integral over the entire volume times the centroid of your infinitesimal volume, xyz, times your increment in volume. And in fact, you could, just like when I started using that table to calculate the moments about a point and the forces and everything, and the first couple of times I did it in the full three-dimensional form to show that the 2D is really just a sort of a contracted version of the 3D, right? Like you can just use the 3D for everything. It's the same with this, okay? Like you can imagine if you have a two-dimensional shape, make your increment of volume just have a thickness of a unit, of 1. And then your z's are 0, and everything falls out to be just like that 2D formula I gave you. Okay. Now there are, okay, any questions so far? There are two useful things to keep in mind about centroids that most of the time you'll be able to use in problems. You won't have to do these integrals most of the time. In 2 dimensions, the centroid has to lie along any line of symmetry of the shape. So for example, say that shape, you're trying to find the centroid. Well, it's going to take some doing to figure out what the centroid location is vertically, but horizontally it's easy. There's a line of symmetry right there, so it has to lie along that line. Okay, so you just cut, so even though you might have to do an integral to solve it, to solve for the vertical position, you just cut the number of integrals you have to do in half, you know. And even better, this means that if you can find 2 lines of symmetry, then where they intersect is the centroid, okay? And then you don't have to do any calculations. And that's what you're doing actually in your head. Well, I'm not trying to tell you what you're doing in your own head. What do I know? But like the shapes that you just intuitively know where the centroid is, like a rectangle and a circle, those centroids are where they are because you have one line of symmetry here on the rectangle, one there, and they meet at the centroid. Okay, and a circle has infinitely many lines of symmetry that meet right here. Right? There's a version of this that works for 3 dimensions too. What do you think? What do you think changes in 3D? Mm-hmm. Yeah, exactly. We're talking about planes of symmetry, and it's not enough to specify 2. You need 3. Okay. So planes of symmetry, and you need 3 of them. The second important thing that's going to be at least as useful as this one is in 2D again. If you can break up the shape that you're looking at into n pieces, then the total area times the centroid really this is just sort of a discretized formula for the definition I gave you, is equal to the sum I equals 1 to n of each individual piece's area times that piece's centroid. Like if you were writing a computer program to approximate a centroid, you would do it like this, right? You do it as a sum of not infinitesimal, but small pieces, right? So that's what we're doing here. But, you know, so if you can, I'll do a couple examples, but if you have a shape like this and you want to calculate the centroid of it, that would be sort of mean for me to give you that, but it's not hard. It just would take forever. You just break it up into a bunch of rectangles. Calculate the centroids of each of those rectangles and the area of each rectangle, and then calculate the total centroid like this. And of course, as you're willing to make those rectangles smaller and smaller, you can come closer and closer to approximating like a curved shape or something. Okay, and two interesting things about this. It works with subtraction too. For example, if you wanted to calculate the centroid of a object like this with a hole in the side, calculate the area and the centroid of the rectangle without the hole, calculate the area and the centroid of that circle, and then subtract the area and the centroid location of the circle from the one of the rectangle, and it gives you the centroid of the whole thing. So that's pretty nice. And second, this one's not so interesting. It's just sort of for completeness. In 3D, the formula generalizes exactly like you would think. Total area, total volume times x, y, z centroid is equal to the sum from 1 to n of the individual volumes times the individual centroids. Anyone have any questions about this? Okay, so once we start using this in problems, like I'm going to give you a couple problems to do where you do have to solve integrals, but like once you start doing real problems with these, I'm going to be done with that, you know, and all you're going to do is use this sum formula. Okay. Okay, so say that you have this T shape. This distance is 0.2 meters. This thickness is 0.05 meters. This width is 0.2 meters. And this is 0.1 meters. What's the centroid of this shape? So, yeah, that's right. So there's two things you can use in this. First, there is a line of symmetry. So right away we know what the horizontal component of the centroid is. I'm going to put my coordinate system right here. Remember, you can put it anywhere, but so the x component of the centroid is 0 right off the bat. Due to symmetry. For the y component, I'm going to break it up into these two rectangles. Okay? I'll call this one rectangle 1 and this one rectangle 2. For rectangle 1, the area is 0.2 times 0.05, which is 0.01, right? And what's the y centroid of rectangle 1? 0.1, yep. And rectangle 2, the area is 0.02. And the y centroid .25. Yeah, you know, just so it's just the coordinate, the y coordinate of this location. The total area is just the sum of those two, so 0.03. So we have 0.03, and we're already done with x. So 0.03 times the y centroid is equal to 0.01 times 0.1 plus 0.02 times 0.25 and so I guess I didn't do that intermediate step, but just solve for the y centroid and you get 0.15. So the centroid is right about here, 3/4 of the way up, which makes sense, right? Like the heavy part is up higher, so you'd expect it to be further than halfway to the top. That's not further than halfway to the top.
Are you sure your math is right?
Nope. 0.2. Okay. Good. uh, okay, let's go with that. Anybody else? Confirmation? Okay, good. 0.2. That makes more sense. By the way, the centroid doesn't have to be on the body. In the 60s, when this American high jumper invented the Fosbury flop, where they go over the high jump bar backwards, it just totally revolutionized high jump. And the reason that it does is pretty simple. They get this huge curve in their back. This really is not an exaggerated picture of what good high jumpers look like. Maybe the part about the segments of their legs being bent like gum. But so anyways, you go over the bar like this. Your center of mass is here. And the best high jumpers in the world actually clear a bar without their center of mass ever getting as high as the bar. Their center of mass goes right under the bar, and they get their whole body over it.
How did they jump before?
They used to jump sort of like they'd straddle it, go over, kick one leg over, and roll over it like this, So you just, all that you'd have on two sides of the bar were like one arm and one leg on each side. And so your center of mass pretty much had to be, there was no tricking gravity. But this way you're sort of tricking gravity. It's pretty surprising actually that you could get your whole body to go over and never have your center of mass reach that height. Okay, let's do another example where you use that subtraction. I'm trying to learn how to use this. Okay. Forget that. I'm only using half of it anyways. Okay. So say that, sorry, that circle is my great white whale. I've done it. Okay, so say the outer radius is 1 and the inner radius is 0.5. And given that this is one of the ones you can just look up in the back of the book, so we're not going to compute this integral, but given that the centroid of a semicircle is 4r over 3 pi, and by the way, I'm just giving, like, a centroid obviously is a vector, but again, we're going to use this line of symmetry. So the only centroid we need is the vertical component, right? So this is the vertical component. What's the centroid? So, like, by the way, speaking of high jump, like in the 50s, there was one guy, this incredible guy, totally unbeatable, who had gone over 7 feet. The world record now is 8 feet. Like, that is a big difference, you know, that just really came from a change in technique. Okay, I'm going to stop talking about high jump now. Okay, so we're going to break this up into 2 pieces, a big semicircle, and then we're going to subtract a small semicircle from it. The big one has an area of pi times 1 squared, so just pi. And its centroid is, if you use this formula, 0.424. The little semicircle the area is pi times 0.5 squared, so it's about 0.7854.
Are we doing just half of the circle?
Oh yeah, you're right. Thank you. So yeah, that's exactly right. So both of these are doubled of what they should be. So 0.7854, that's 0.3927. Is that right? And the y centroid of that one is 0.212. The total area is pi over 2 minus 0.3927. Could you subtract that?
1.178.
Okay, so 1.178, the total area, times the y centroid is equal to 0.3927 times the centroid of the big piece, 0.424, minus, this should have been, this is the area of the big semicircle. So that's 1.57 minus the area of the small semicircle times its centroid. So 0.3927 times 0.212. Can you solve for that?
It's 1.57.
That's the answer.
No, what is?
That's pi over 2.
Oh, because you take the size of the whole thing. I see. Yeah.
Yeah, right. This is the right. This is the area of the whole thing before you subtract anything. Yep.
I have 0.494.
0.494. Okay? That makes sense. So taking out the material near the center actually makes the centroid higher than makes the centroid higher than it was before you took it out. And this is like a little approximation of a high jumper. If we can, from now on, every lecture will be based around high jumping, because the you can see that centroid is just below the just below where the material starts, so it's off the body there. Any questions about that? That's right. Okay, so that's how to calculate centroids. There are two uses for them: calculating centers of mass and calculating distributed loads. Distributed loads we'll talk about next class. But as far as the center of mass, you know, it's a lot more common that you're going to deal with homogeneous materials. But if you do ever have to do a calculation that involves more materials, the formula for the center of mass really technically is that the total mass of the object times the center of mass location is equal to the integral over the full, you know, object times the increment of mass times the location of the center of mass of each increment. And you can see how this would reduce to that centroid formula. Like if the whole thing is the same material, mass is just equal to some kind of areal density of mass. And then you can just pull that density right out of the integral and cancel it on both sides, right? So it reduces to the formula we had. You also can do the sum formula that I don't have room to write in here, but you can hopefully imagine what that is. It's just identical to the centroid sum formula where you break it up into pieces, except you're dealing with individual masses instead of individual areas. Okay, that's it. So I would suggest get to work on those practice problems as soon as you can.